Hey Claire, what's up?
Hi, I'm doing good. How are you?
I'm good. Are you hanging out in space?
No, yeah, I just usually have a black background because
A lot of people really like, I don't know, a lot of people are like really crazy about UWorld and about finishing
mm,
UWorld, but um I think that finish like if your objective is to just finish UWorld, you might like end up skipping some stuff or
mm,
not like really understanding it to the level that that you should be
mm.
understanding. So like for instance, let me see. Um okay, so you could tell me a lot about just that that word. What can you tell me about this word?
So like it requires like a ligand to bind onto the receptor and then that allows ions to flow through.
So let's say the ligand could look like this. Let's say it could look like that. What do you think it might look like?
Um,
And just from that.
hmm, I guess so it probably wouldn't be hydrophobic because then it would be able to flow through, so probably the bottom one.
Exactly. Perfect. So yeah, ligand gated ion channels are going to involve ligands that are going to, be some kind of like polar, like it's not going to be able to just travel through the lipid membrane. Good. Um, a couple of other things I see here, like okay, if there's a subunit that's mentioned, um, what what can that tell you about what they're talking about?
So this channel is probably like I guess there's like multiple subunits. So, I mean, quaternary structure is also one of
Exactly.
those too.
Yep. Quaternary structure. Perfect. So that's the way that yeah, that you want to be able to read these passages. I mean, like on the test, obviously, like, you're crushed for
Mhm.
time, so it's going to be something that we like work on like over time. But yeah, that's the type of like deductive, reasoning um that they really I can't even think of the word that they really like you to have
Mhm.
on this test. All right, awesome. Cool. So, all right, you said you had a question on this one?
Yeah, like this one I didn't honestly really understand. I think it had to do something with, or I guess I could try to like walk through like how I went through this question first. So,
Oh yeah,
um,
I should ask you that. So,
mhm.
how do you usually like
Mm,
I'm guessing it seems from like the highlighting that you do read the passage first, which is good. And then you do like the questions. Now, do you like select a question, check the answer, or do you like select the question, go to the next question, and then you're
yeah, for
done?
UWorld, I do like the tutored mode where like each question I would like check and then review
Uh-huh.
and then move on. Yeah.
Okay. Let's try to do it like if this is 7 to 10 questions, just do the 7 to 10 questions on your own because if you're let's say if you do question 7 and whatever you look at the answer, it's gonna likely influence your answer choices
Mm-hmm.
for the questions that come after, and that's not what we want to do. Um, but okay, that's an easy fix. So okay, so when you saw this question, like yeah, walk me through, I guess,
Yeah.
your thought process.
Mhm. Yeah, so okay, so I read this like PKA, so I'm just kind of like directly looking to the passage for something related to PKA, and then I saw like pH of 7.4, and how the glutamate residues repel each other, but under acidic conditions they form stable bonds. So then looking back at the question, I don't wait. Compare.
Okay, so this is another super common thing.
Mhm.
Um, so almost everybody that like I tutor for the MCAT, they kind of treat this as like a word search.
Mm,
Like if you see the word, I don't know, you said you saw the word like pKa,
yeah.
then you kind of look through the
Hmm.
passage for maybe a word that sounds like pKa or something like with glutamate. And you'll see that most of the time that's how they generate the trap answer choices. Because like if you put your if you go into the mindset of the person making the test, it's not like you're just gonna make like two answers that are kind of close and then the rest are just obviously wrong.
Hmm.
So that's gonna help also because we want to know like not just like if you're making a mistake and not just if you're making a mistake like how to fix it, but to know like and classify like exactly what type of mistake you're making. Um, but I would say that I mean, you're probably doing this already automatically, but a lot of times the MCAT questions, like it's a question within a question. Like to understand what the question's asking,
Hmm.
is like half the battle. So
Hmm.
let's think about like what is this asking us?
Mm. Yeah, so I guess the question is like saying, so we're trying to compare the pK of like free glutamate versus what it would be um when yeah, it's in the binding pocket of the enzyme.
Tell me about glutamate.
So glutamate is one, it would be like negatively charged
Oh,
because it's like an acidic side chain.
all right, and tell me how that makes it negatively charged.
Um, so like in I guess like a pH of 7, right? Like the physiological pH, which is higher than its pKa. That means that there's not like a lot of free hydrogen protons around, so it would be deprotonated because like the pKa is the boundary when it goes from like protonate to deprotonate, and it's higher than that, so that's why it would be negative.
Yep. So it always depends on, I guess, like so pKa is usually what we can use to measure like a molecule. It's like kind of like pH, but it's like intrinsic to that molecule.
Mhm.
And pH really just comes from, like the autoionization of water.
Yeah.
That's where like that comes from. So you could think of it like this, or like at least this is what I think of. It's like, okay, let's say this is a beaker with a pH of 7.4, and I have some amino acid with let's just say some pKa less than whatever this pH is, and we just threw that in there. And then you could just think, okay, this amino acid, it's entering into a more basic environment or acidic environment.
So it's entering into more like basic environment.
Yep. And that's just relative to the pKa, right?
Hmm. Yeah.
Okay, cool. So, um, all right. So,
Um,
yeah,
okay, I see. So I think yeah, I was just kind of lost on like how to use like the 7.4, but I think now I'm so like this the pH of like the ligand binding domain is 7.4, which is more basic than like what a free glutamate is. So that's why it would have um yeah, I think I was also stuck in this because I thought that the pK of an amino acid wouldn't change, like it's just a property of the amino acid itself.
that's actually a good question because I did just kind of describe it as like an intrinsic kind of thing. But um, you know how like the induced fit model?
Yeah.
Like people used to think it was like lock and key, but it's
Mm.
like induced fit. So it's like so the microenvironment of like that active site or wherever, molecules bind to one another could affect that pKa like ever so slightly just so it can kind of like fit into that active site. So um so that plays a role here. But I think this is talking about let me actually read it. So, all right, based on the okay, glutamate residues. Okay, so they are not the ligands. They are the things in like the ligand binding pocket that gets ionized and therefore repel each other. And that's at a pH of 7.4. So that's going to be when I guess glutamate gets deprotonated. Oh wait, well I guess that's what we have to find out. But and then I guess under acidic conditions, um, they get protonated. So I guess they'll just exist as like a Zwitter ion or something like that, and they can make stable hydrogen bonds. Okay, let's see. How do the pKa values of these residues most likely compare to the pKa of free monomeric glutamate side chains in solution? Okay, so what is this? Yeah, what is this asking us here?
Yeah, so like I guess comparing so these are actually the pH values, not of the ligand itself, but of the binding pocket that contains glutamate. So um
Yeah, so there's the pKa of the free glutamate monomeric, it's not attached to anything else.
mm,
Um and then they're asking you to compare that to the pKa values of the glutamate like residues that are at that ligand binding site, right? So
mhm,
they're telling us that at the ligand binding site, the glutamate is ionized, right? And under, I guess, acidic conditions, it just becomes like I would assume like a Zwitter ion. Not sure if they say anything else uh, about I guess anything about it being free, like what it would be if it was not attached to anything, right?
mhm,
Okay. So I guess we're trying to compare um at a pH of 7.4, glutamate is ionized and it's probably going like it's likely going to have a lower pKa than 7.4, so it's going to be negatively charged. It'll like lose a proton. Um and then the free one, they're saying free monomeric side chains in solution. So like that would be a Zwitter ion then, right?
mhm.
Like with a negatively charged like C terminal, a positively charged N terminal. So so I guess we would just have to compare those. So we know that they can't have the same pKa because otherwise they would have like the same charge, right? So
Mhm.
there must be a difference in pKa, and D is kind of weird. I mean, like that kind of choice is always weird. Like I don't want to ever tell people like never choose that. Um, but we definitely know that something is different, and that could lead us to eliminate C, and we could probably figure out something about A and B like easier than we could figure out something about D. So then it just becomes is um the ionized glutamate, is that going to have a higher pKa or a lower pKa than just the regular glutamate? Um and also you don't have to like, well, it could help to like memorize the pKa values of like the different amino acids, but But you know from like the name glutamate that it's acidic, right?
Hmm.
So chances are that this ionized one over here probably has a pKa that is less than its like monomeric counterpart, right? So that would account for the different pKa's that they would have. With the pKa in the acidic, oh sorry, the ionized glutamate, since we know it's ionized, that can help us figure out that it's gonna have like a net, negative charge. And free glutamate, we know since it's an acidic amino acid that it's likely gonna have a pKa that's going to be less than 7, typically like less than 7. So that could be a way that you can uh get that one as your answer. There's going to be lots of different ways that you can like come across the answer. Um and it's always good to like have contingencies, but okay, so you were telling me that you're thinking like that pKa wasn't something that changed, and like that's a fair thing to think about. But I guess when they ask you a question like this, um you know, aside from like one choice, like the rest are saying that they do change. Um, yeah. Oh, and did you want to show me something here?
Oh yeah, I think it was just also they kind of mentioned how like pK can change if local effects alter the stabilities of the products and reactants.
Yep. Hmm.
Mhm. Yeah, okay. I think that makes more sense now. Um, But yeah, I was also wondering, yeah, like if we can kind of like walk through some problems through like in the CP section of Jack Westin.
Yep.
Mhm. So like I guess we can start with mm, this one understood. Understand. Yeah, like this is a physics 2 one that I just didn't really know how to do. Um
Oh,
yeah.
okay. So let's see. Physics 2, that's like electricity, magnetism, right?
Mhm.
Um, okay.
Yeah, so I knew it kind of maybe had to do something with like the direction of the electric field. Like I vaguely remember
Did you ever
there's
do like the right hand rule?
yeah, I honestly I couldn't remember like which one goes with which, so I didn't have enough time to like figure it out.
Got it, got it. So the entire reason for it, if you think about
Mhm.
it, is because once you introduce electromagnetism, um, it starts to be three-dimensional,
Mhm.
and there's no way for us to like draw something really three-dimensional. So using a three-dimensional thing like our hand can really help. So generally, that like it could just be like if you just like do like a karate chop kind of like this, your
Mhm.
thumb we can say is going to be um, the direction that a charged particle is moving. And that could also be equated to current. And the direction that the rest of your fingers are pointing,
Mhm.
that's going to be the magnetic field, like if there is an external magnetic field. And
Mhm.
then the direction where your palm is like facing outwards is going to be it's like something called the cross product. It's basically um multiplying the vector of the moving electron with the magnetic field to figure out the magnetic force that electron is experiencing.
Mhm.
So that's so that's the right hand rule. Oh, and there's also like a modified version of that where it's like where you do the curl.
Mhm.
And that one, it's kind of like it's similar. It's like your thumb is also going to be the movement of the charged particle, and but your these fingers are going to be also the magnetic field, but they the idea behind the curl is it's like if you had, let's say, a wire with a current going this way, and I do this, I could have a magnetic field on the right side of the wire going in, and then on the left side coming out. I honestly always forget like which one is um oh, okay. Sorry. The dots are the ones that are coming out of the page. So dot dot x x x. So yeah, that's just the other version of the right hand rule. So okay, so yeah, tell me about, you know, how you approach this. At like what point did you
Mm.
like feel like what are they talking about?
Yeah, okay. So if proteins or protons are moving counterclockwise,
Anything in the
mhm.
passage?
um, honestly for CP, I also don't really read the passage at first. I kind of just like jump to the questions and then look back.
Yeah, I'd say like
Yeah.
that could be something that you could do in CP if you're like really running out of time.
Hmm.
Um, I would say it's probably not going to work for any of the other sections, but yeah, if you're running out of time, you can get away with it in CP.
Hmm.
Uh, all right. Yeah, okay, so yeah, go
Yeah.
about it the way that
So,
yeah.
counterclockwise. Um, I think I remember something about like the force, like the centripetal force, perhaps, and how that can lead sometimes to like a circular arc. Um, and that's maybe produced by the magnetic force. And then I'm seeing in the diagram that the electric field itself is pointing right. Um, yeah, I guess I'm just kind of like stuck from there.
All right. So let's see. Okay, we have an electric field that's going from left to right. Does that like tell you anything about it?
Mm, I know that there's like an equation that's like force equals to, wait, no, electric field is equal to force over the charge.
Oh,
Um,
just for the field lines, like for instance, they're
mhm.
gonna go just by
Oh,
convention. Um, yeah,
right, because
positive.
electric field lines point away from the positive charge.
Mm-hmm.
Uh-huh.
Yep. So, okay, good. And so yeah, this big arrow is basically the direction of that electric field. So let's say you had something like a proton,
Mhm.
like and it's just there. What do you think will happen?
So like it'll move to the right.
Yep. Because it'll be repelled by the stuff on the left and it'll
Mhm.
be attracted by the stuff on the right.
Mhm.
So that's just using an electric field to, well, you're putting a charged particle, which means it's sensitive to an electric field, and you're using the electric field to accelerate it, right?
Mhm.
Um, and this is actually something called uh something called like a velocity selector, like basically like over here in the source, like you would just have like a regular atom. You shoot some ionizing radiation at it, like some high energy electromagnetic waves. They'll talk about this a lot. It'll be like gamma or like, UV or something like X-rays or something like that. But it'll strip away electrons, causing it to become charged, like this positively charged particle. And I mean, if that didn't happen and you just had a regular atom that's neutral, like nothing would happen in here.
Mhm.
But now that you have like a charged particle in there, it's now sensitive to this electric field and it's going to start to move. Okay. And they're all like, this stuff is positive too, this stuff is negative too. So this stuff, these will all move, but this little hole here makes it so um that only the charged particles that are in that trajectory that kind of lines up with that like little gap, only those can actually like not just accelerate, but be able to leave this entire like acceleration chamber. Um, okay, now I don't know if they are going to talk about this after, but what typically happens after this though is so okay, we have an electric field here, and you could also have both wait, do they have anything where there's like they have both like an electric field and magnetic field in that same diagram? No, right?
No, I think they were only showing electric field.
Okay, okay. Because usually, um, okay, so let's see. Okay, I'll just do it like this. So, well, okay, do they talk about, okay, magnetic field? This is just something that they just mentioned there, or okay, got it, got it, got it. Um, okay, so either like it's inside of this, which they didn't draw, or at the very least it's outside of it. So, okay, let's say we had a magnetic field outside, and this is the one that goes into the page, right? So what you can do is you can since the magnetic field that I drew, the X's are going into the page, I'm going to put these fingers like as if it's going into the screen. And my thumb is going to be the velocity or the current or the direction of that charged particle.
Hmm.
And then my palm is facing upwards. That will be the force, the magnetic force that this charged particle is going to be experiencing.
Hmm.
Now, usually inside of this, there's also a magnetic field, and that's because that's like kind of like the only way to have it move straight in this way. Um, but we could just go right into this, magnetic field thing here. So if this force, the magnetic field force is moving upwards like this,
Hmm.
but I'll use some different colors. Okay, magnetic force here, velocity is still here, and like the resultant, like when you add vectors.
Hmm.
So that would be like here, right?
Hmm.
Right? Because you already have the velocity here, and you have the new um magnetic force here. So this is going to kind of rotate like this.
Right, so this is the like kind of centripetal force maybe that I was talking about earlier. Yeah, and it makes sense that I would have to point up in order to make it counterclockwise.
hmm So now
So yeah.
so now its velocity is up, but tell me about the magnetic force it's experiencing.
Yeah, so like this upwards green arrow would be the magnetic force.
Uh-huh.
And then that would be equal to like V over R squared, or was it MV squared over R? Forgot.
Oh yeah, don't worry about that.
Mhm.
But where would the the magnetic force vector be?
Like this upward arrow.
So that's what it was there.
Uh-huh. Oh, you mean okay. Like it would point inwards, like into a circle.
So you could just do the right hand.
Hmm.
So
Yeah.
velocity is up, right?
Hmm. Okay, and then the field itself is like pointing inwards, so the okay. Let's see.
So this way, right?
Uh-huh.
And so this is going to be the resultant here. So it's going to move around here until it gets here. Here, this is the velocity. Where would the magnetic field be here? I'm sorry, the magnetic force be here.
I see. So if I do this, so it's pointing down.
Yep.
Okay.
And so this is the resultant, and then same thing here. This is going down here, and that would be the magnetic force that it would experience,
Uh,
right?
so actually, the magnetic force would technically change directions as the velocity of the particles also changing directions to keep in a circle.
So the
Okay.
velocity, let me ask you this. Would the speed change?
Mm, I don't think so. Yeah, it's just the
Let me know what
direction.
you think. Yeah, just the direction, right?
Hmm.
Okay, yeah, so the speed doesn't change, and neither then would the kinetic energy.
Hmm.
Because even though kinetic energy has velocity inside of it, which is a vector, which does matter, like direction matters for that, it's a squared v. So any, sign difference, because we use signs to indicate direction, like any of that stuff will just go away. So
Hmm.
yeah, the velocity changes because it is moving, it's changing its direction, but the magnitude of the velocity doesn't change, aka speed. The kinetic energy doesn't change. And yeah, you end up getting this circular motion. And you could even connect that with, so for instance, there's like this, like for the centripetal force, and you could equate that with what is it? Q V B wait, QVB. Sine theta, and you could just essentially divide the velocities on both sides to ultimately get, I mean, the sine, if it's usually going to be 90 degrees, so the sine term is going to just turn into one. So you'll just get this over that. So that's the radius that this charged particle um rotates about in that, strictly speaking, magnetic field after it's already had velocity. Um, and this way we get to see, and also with like equations and stuff, you want to be able to, like, it's not the most important thing to like have, I mean, yeah, to be able to do this, yeah, but to be able to see things in proportionalities, like, for example, I could see, this is the symbol for proportionality. I could see that the radius is inversely proportional to the mass. And you see how I did like radius, proportionality symbol, 1 over mass? Because sometimes people do something like this, like radius goes up, mass goes down.
Hmm.
And like, I would say not to do it that way just because they like to ask like what these like mathematical proportions like would look like if you graph them. And also when you're like manipulating the equations and stuff. But this is showing us that there's an inverse proportion between the radius and the mass of that particle. So if we took I'll use orange. So let's say we have an orange one, and let's just say the orange one, well, I'll actually do it like this. So let's just say there's like a wall here, wall here. Okay, so, and then let me do the pink one. Okay, so the pink one like hits that wall more closely, right? Compared to the orange one. So what do you think that can help us?
So the orange one would be lighter, like less mass.
Yeah, so yeah, because it's gonna be deflected more. And so
Mm.
this is actually how a mass spectrometer works. Like back in the day when, like the Manhattan Project.
Mhm.
So like what you like atom bomb, that kind of stuff.
Yeah, yeah.
So like we have to separate like uranium 235 from 238. So this is what we did. We put like a little container here for uranium 235. We put a little container here, or the other way around, for uranium 238. And and yeah, having as much of like making as many connections as possible. Like you probably learned it in like your neuro class, like elaborate rehearsal.
Mhm.
Yeah, having as many like salient things that can help you remember stuff instead of it being just a bunch of like kind of disparate things is always going to work in your favor. So,
Yeah, makes sense. And then is the reason we know that there's like a magnetic field afterwards, like here, because it tells us, or like is that just an assumption that we make?
oh yeah, yeah, I was trying to look for that because
Mhm.
I drew it and here they just said that,
Yeah, and I guess if the question is asking what direction the magnetic field is
oh,
pointing,
let me see.
maybe that just means that we had to like assume. And also because I guess here it says utilizing magnetic fields.
Okay, okay, okay. Yeah, yeah. It's pretty weird because like honestly like this thing inside of this should
Mhm.
also have like magnetic field, but whatever. So let's see. Okay, they're saying protons, so we know positive. They're saying counterclockwise. They're saying CYT. CYT is something that, oh, it's a cyclotron, but it's something that involves a magnetic field. So yeah, we would have to use logic to uh figure out what direction that magnetic field is from them saying counterclockwise. Yeah.
Okay, that makes sense.
Mhm.
Yeah,
Oh,
and
and
then this
there we
is
go.
another one. So the card magnetic field strength. We
I
modeled. Oh,
think
okay. So
we did this one, right?
right, yeah.
So that's it. Yeah, and that's another thing. You're gonna get to the point where like you're going to be able to anticipate
Mm,
questions. Like you're yeah, you're going to get to that point.
got it. Mm, this one's a mistake. Okay, so this one, um, I guess I'll also just kind of maybe talk through how I thought of this. So there's so they dissolved this water and then they added this to this and then precipitated this out, iron oxalate dihydrate salt. And then we're trying to determine what type of reaction that is.
Hmm.
So yeah, I guess I probably just honestly guessed and thought it was single displacement, but um hmm,
Okay, let's see. So this thing has iron in it, right?
mhm,
They have this oxalic acid, which doesn't have iron in it. They
mhm,
precipitated something with iron in it, like that, and something with oxalate in it, which
mhm,
I guess is something from there.
mhm,
So. So you could kind of think of it as like the iron thing, and then I'm just gonna use an X for the other part, and then I'm just gonna say ox, and then a Y for the other part. And then if this gives you something with iron in it and something with the ox in it, right? It has to be a double displacement because we're changing two of these things, right?
Oh, okay.
Hmm.
Okay, I think maybe what happened was like read this as like there's only one product that's formed. So in my mind, I was like, okay, single displacement, but that makes sense.
Yeah, I mean, there's also water
Mm,
and hydrochloric acid.
mhm.
Um, but yeah,
Makes
you
sense.
could think in like on that like atomic
Mm.
scale.
Okay, this was, I think the next few are all, yeah, torque problems. Um, so this one is,
What can
mm,
you tell me about torque?
yeah, so it's, oh my goodness, it's like the force that makes things like rotate around, I guess. And then there's like um, like if this is the axis, like wherever the force is like pointed at, like this is kind of the distance, you multiply that by the force, and then that like makes the thing rotate.
Hmm.
Yeah. And then there's
So
also
if I'm turning this page,
mhm.
am I doing torque?
Mm, I wait, yeah.
So let's see, right? Because torque is going to be a force times some distance. I'm just going to
uh,
write R. There could also be force times distance, like with a D. What could that
mhm.
be?
Like that's the distance from the axis of rotation.
Oh, just for like if you saw FD.
Oh, work.
Okay. So they look very, very similar.
Hmm.
How are they different? Maybe there's something else in the equation that.
Yeah, I think the first one needed like the sine, I think, or cosine. No,
Hmm.
yeah, sine.
Okay. And yeah, tell me about that.
Mm, so I think that's like the angle between the axis and the force that's being applied, maybe. Yeah.
So like let's say we go from 0 degrees to 90 degrees.
Mhm.
Um, what would sine of zero be?
Sine of zero is zero.
All right.
Yeah. And then it
Uh,
goes to one.
mm-hmm.
Oh, right.
Right.
And then that's why, like, if the force is directly perpendicular to the
Yes.
axis, that's like the most torque that you'll get.
Yes. So these are pretty much the same exact formula,
Mhm.
but I could rewrite this with like a little subscript here. It's not an 11, it just to mean parallel. And then here I could just put a little perpendicular sign. So torque and work are super, super, super similar, but you rarely like you can't, I mean, if you have some angle, like they're not going to really give you like angles that I mean, they'll give you angles that'll make it so that this turns into one or like the cosine turns into one.
Mhm.
Um, but yeah, if you have any situation where like let's just say this is some door with like a hinge or something like that and like a doorknob, if the angle if your force vector is yeah, so you want to I'll just write D even though it could mean R. So if the angle between the force vector and the distance is 90, aka perpendicular, it's going to produce a torque.
Mhm.
And generally, they'll include a hinge of some sort or a fulcrum just so that torque like rotation thing can actually happen. Um, but work is usually something like I usually draw this. It's like you're applying a force to, let's say, this object, and the object, let's say, moves this distance d.
Mhm.
And so the angle between the force and the distance d is zero, which means cosine turns into one, and you just have the FD, and that way you can have work.
Mhm.
And um and like with the exception of sometimes they might like combine the two, for the most part they're completely different things. Like if you are opening a door like this, um like if you imagine to open this door using, let's say, work, like let's say you're pushing this way or this way, because that way the force vectors would be parallel to this door. You wouldn't be doing any torque and you wouldn't be able to open a door.
Mhm.
And like the same thing, I guess, with this box. Like if you push down on it like this or something like that.
Yeah.
So yeah, so that's yeah, so that's torque and work. Okay,
Okay.
cool.
So that's why,
Hmm.
yeah, like I guess if
Oh yeah,
you
so
that right, yeah.
this is yeah, and it's like like a sliding door.
Hmm.
That's you're using work rather than torque there.
Mm. Oh,
Oh,
okay, I see.
what about that proton in that previous example? Is that
Mm.
work or is that work?
So that would be wait, that would be considered torque.
Yep.
Yeah, so no work is being done because it's not moving parallel to the okay.
Yeah, it's kind of weird, right? It's like
Mm.
the moon, the Earth's not doing any work any work on the moon. Um, it's doing torque.
I
All
see.
right, cool. All right. Yeah, sometimes it can get really annoying with these types of questions with like, this type of formula, but what it can always help to think about like what does it look like?
But yeah, it looks like the regular like velocity. It's just like everything's in angular terms.
Exactly. Yep. So it's just like, this like
Mhm.
kinematics formula. What would be on this side?
That would be like distance.
Yep. I usually write like delta S because you could have an X, a Y, a Z,
Mhm.
but you could use whatever you want. So okay, they're talking. So okay, so now we know that because when they show us something like this, it's like, yeah, they want to psych you out, but even if you haven't seen it before, you can tell like, okay, I have an idea of what this is kind of telling us. Okay, let's see. Equations involving rotational components of motion generally mirror their translational counterparts. What do they mean by that?
So like if you were to translate this into like the general linear motion, like is that kind of yeah.
Yep,
Mhm.
like that, right?
Mhm.
Perfect. Okay. For example, the change of angle is related to angular acceleration. Okay, it's like the alpha. And the angular velocity, this thing, um, via the following equation. Okay, we have that there. Let n be the number of rotations each object makes when traveling the complete distance of the ramp. Which of the following expressions is equal to the average torque experienced by the solid cylinder? And then they say the, I guess, omega or something. WT is negligible. All right, cool. We don't have to care about that.
Oh, I think okay, so
Oh, maybe
this
you
the
do.
torque is equal to moment of inertia times angular acceleration. So maybe I think we are supposed to isolate wait, was it ever or like I think yeah, maybe isolate this variable. We can kind of represent this like distance using the number of rotations because that would be like 2 pi.
Mhm.
And um so yeah, I guess that and then the moment of inertia. I don't know if we have to take that into account, but
Oh, that's the ramp they're talking about, right? Okay.
mhm.
Let's see. Okay.
Yeah. So
Oh,
if
let me see a little bit on the left.
oh
All right. Solid cylinder, solid sphere, hollow cylinder, hollow sphere. Okay. Oh, and then okay, and then they give us moment of inertia. Okay. What do you think could account for these differences? It seems like
mm.
the yeah.
Yeah, I think if I remember, it's moment of inertia was like dependent on like I guess how hollow or like filled up the object is, and also like the shape of it, maybe, or like how distributed the mass is
hmm
around that particular
hmm
object.
Yep. Yeah. If you had like a yeah, like a hollow thing like that, the
Mhm.
masses are like concentrated at the edges.
Mhm.
So if we were to kind of do like this like maybe like radius thing, there's going to be more mass at the ends of it, and that's going to give it a lot more, that's going to give it a larger moment of inertia. So it would make sense for the hollow ones uh to take more time um to roll to the end of the ramp, and it seems like they're telling us that it is rolling down. It's not like just sliding down. So
Mhm.
that means we can't just use like, like a friction kind of thing. But okay, let's see. Let n be the number of rotations each object makes when traveling the complete distance of the ramp. Okay.
Yeah, so I like isolated the term now, and so I got the angular acceleration is 4 pi n over t squared, which
Mhm.
is one of the answer choices, but I think we still have to take into account the moment of inertia, which this one is, I guess, does it tell us? Oh, a solid cylinder, so times 1/2 um mr squared. So that would give me 2 pi n mr squared over t squared, which is a.
hmm
Yeah, I guess maybe I was just in very much a crunch of time, so I didn't like have time to fully think through it.
Oh yeah. So yeah, another thing I would say,
Mhm.
whenever you're doing your like time practice test,
Mhm.
like it's fine doing it that way, but when you have it like scored, write down, like try not to look at the answer. It's fine if you can't
Mhm.
help it, but write down which questions you got wrong and then do something called a blind review, which
Mhm.
means you redo the test. You don't do every question though. You redo just the ones you either got wrong or you like maybe you got it right by guessing.
Mhm.
Because then that gives you that takes so because anytime you get a question wrong, there's two like variables, right? There's time and there's, did you know it or not?
Mhm.
So if you just look at the answers right away, then you kind of almost waste that question.
Mhm.
So I would say, yeah, if it's something that, you couldn't get because, you're running out of time and stuff like that, on your second like pass through, um, yeah, try like do it untimed, just the ones you got wrong, and see if you can figure it out. If you can figure it out, then you're good.
Got it. Yeah, makes
hmm
sense.
And I
Mm.
guess also like some kind of patterns can also help
Mhm.
there. Like for those equations, like I'm sure a couple of them, just if you could go back for a sec,
Mhm.
like I see like r squared on top. So I see t squared on the bottom, for everything.
Mhm.
I see m on the top for two of them. I see r squared on the top for two of them, n on the top for all of them. And then, well, pi for all of them, and then we have 2, 4, and 2. So that could be a way. I mean, you figured out like which correct pi thing to use. Uh,
Mhm.
but yeah, also if you're like, strapped for time and stuff,
Mhm.
you can use that as well. Yeah.
Makes sense. Yeah. And this one, I guess it kind of relates to what we were talking about, but okay, underestimation. So using the equation, um, that means either the force itself was like underestimated or the moment of inertia was overestimated. So yeah, I guess D would make sense because C using a solid sphere has oh wait. Solid sphere actually has a greater moment of inertia.
Oh yeah, yeah. I hate
Mhm.
these types of questions because it's like they're either saying that the data that they have is an
Mhm.
underestimation, or that the new data that you're trying to find out is like the actual underestimation. So it can be really tricky like that. Um, so okay, let's see. Experimental errors in figure one underestimated the calculated value for the angular acceleration for a solid cylinder. So we have that, we have time. Okay. So let's see, using a solid sphere instead of a solid cylinder with the same mass and radius. And so I guess were you like between B and C?
Um, I think I don't really know like what I chose C,
Mm-hmm.
but yeah, I mean I don't know why I cross out D because D definitely makes sense too. It's like if anything, I should have been stuck between C and D. Oh, hold on. I guess it's C wrong because like if the experimenter like kept assuming that it was a solid cylinder, they would have used that equation regardless. And then since the mass and radius are the same, I guess that wouldn't lead to an underestimation.
Yeah, so yeah, it'll be some type of where's my thing? So like some type of experimental error.
Mhm.
So I mean, I guess this can be one, this can be one, this can be one. This one is a little weird because when they say the same mass and radius, like they don't really tell us if they're using like the correct, like if they're for the solid sphere, if they're using like the correct solid sphere like
Mhm.
formula. But yeah, these can be tough. So I would just, I guess, think about it being an experimental error, and you can think about if the actual value that they got for the solid cylinder ended up being um lower than it actually is, right? Then maybe they're doing something that is going to increase one of these. Well, wait, they both have r squared, but they should have the same r value, I think, right? But the only other thing that I see that's different is are the numbers in front of them.
Mhm.
So yeah, I think that's a way that you can figure out that can give you that underestimated um angular acceleration for the solid cylinder.
Mhm. Yeah, and I guess like so B, I'm just trying to think like how that would affect it, like
Mhm.
measuring H be larger than what it actually is. So I guess would that affect the angular acceleration component? Wait, yeah, maybe because it would have more potential energy at first, and then
So yeah, it could have more potential energy, but it seems like since they're measuring like angular acceleration,
Mhm.
like like it's gonna accelerate as it falls down, like down this ramp, and if it's accelerating, its velocity is going to increase. So if you measured h to be larger than what it actually is, you're probably going to get a smaller, velocity at the very bottom. Or the other way around, if you measure it smaller than it actually is, you might get a different velocity, but the acceleration will always be the same, right? Like if you imagine dropping something out of a window
Mhm.
or dropping something like on the floor, I don't know, on the ground outside, um, like the thing that you dropped out of the window can get faster because it has more time to experience acceleration, but the acceleration will be the
Mm.
same for them, right?
Mhm. So I guess like if I was to compare like a ramp like this height versus this height, and I measured the velocity like here, for instance, like at the kind of at the tip, the one that started off higher would have like a larger velocity down here, but for both of them, the oh my gosh, the acceleration is the same. Oh yeah, and I know that we're kind of over time, so I don't know, like should we stop here or
Uh, one sec. Let me send. It's okay. I just sent an email, but all right. Sorry, what were you saying?
oh, just like in terms of like time, like right now, like should we probably I guess end here or
We could do another one.
okay. Yeah, this is I guess the last one about like torque too, but I think I was also on a crunch for time, didn't like
Hmm.
have enough time to think through this, but moment of inertia. So um okay, forces in terms of newtons, which also can be written as kilograms over um wait, F equals M.
Hmm.
Okay, kilograms over second squared. And then angular acceleration.
Anything else there?
Mm, F equals MA. Wait, oh, meters.
Hmm.
Okay. And
Yeah. So
then, mm,
anytime, yeah. So anytime you want to find out the units of something, you can use your knowledge of the formula. But if you don't remember the formula, you could also use your knowledge of the units
mhm,
to figure that out. But yeah,
mhm. And then angular acceleration would be in, I guess, radians over second squared.
yeah,
Um,
it could be
and
like that. It
then,
could also be like like if you didn't want to use like radians and you wanted to actually use like some distance, it could be like the circumference or something like that.
mm, um, yeah, so then I'm getting kilograms times meters over radians, but there's no radians in the answer choices.
Hmm.
Um, hmm.
Uh-huh.
So to put radians in meters, then that would be like, oh my gosh, what's a radian equal to? Um,
So yeah, yeah. Usually radians aren't going to like really come up in
mm,
like they'll do something with like 2 pi like 180 degrees or 1 pi or something like that to get it into like degrees or something like that. Um, but over here it seems like okay, we have some mass term, we have some radius term that is squared, and it seems like that's the case for all of them.
Mhm.
So so we know that there has to be a mass term, and this, and this all have mass terms. C has one too, but there's a joule in there, and
Mhm.
that can't be there. So we could rule that out. And then let's see, R squared, and R is just some measure of length, so that would just be like meters. And since it's squared, it'll be meters squared.
Oh. Oh, I should have just looked at that. I don't know why I was trying to do it from scratch from like F equals to.
Hmm.
Huh. Okay. Yeah. And I think I see like a lot of these like type of unit credit questions and I always
Yeah.
kind of tripped up. So like what are some I guess other common ones that like you see or things I should know?
Yeah, so like so it's like dimensional analysis.
Mhm.
Yeah, I would say like that and like uh like the cars section, like the critical like, reading section are two of the most like important skills you could have for this test.
Mm.
So be really, really, really comfortable with um like deconstructing units, being able to see like a joule,
Mhm.
right? We can think of that as like, well, we can think of it as without like just going to the answer. Okay, what is it a measure of? It's a measure of energy. All right. Does that mean I'm going to use this form of energy or this form of energy? They're all energy, so they're all going to be just fine. So this one is going to be kilograms times meters squared over seconds squared. And I can actually even deconstruct this. Kilograms times meter, well, times meters per second squared is force, right? It's a Newton.
Mhm.
And this extra meter square is if I multiply by another meter, which will give me ultimately Newton meters, right?
Mhm.
And that's a joule. And then if you did a joule per second, that'll be power, which you could think of as like the rate of change of energy, or like how much energy is like lost to the environment over time. But yeah,
Mhm.
there's if you yeah, it seems like you have uh Jack Westin open, but they have lots of stuff. Yeah, so on the Jack Westin website, if you go to like um you can like open up a window and just like open up Jack Westin, I'll show you. All right, let's see. Oh, this looks kind of different.
Yeah, I think they updated it.
Let's see. Let's scroll down. Okay.
Is it like an outline or?
Okay. Get rid of the dashboard part in the URL up there. Yeah. Oh, scroll down.
I don't know. Oh, say like something I should search up maybe?
Okay, let me see. So there's basically a bunch of like question sets that they have that are
Hmm.
called things like physical discrete set, chemical discrete set.
Oh, I think it's like the question bank probably, and then
Oh wait, go scroll down a bit.
mhm,
Okay, yeah. Here,
mhm,
this is it. All right, over here for sections, yeah.
CP,
Um,
and then
oh yeah, let me see that again. Sorry for the sec, yeah. Because it'll be the CP discretes
mhm.
below that. Yeah, right there. Yeah. Yep. So you have like these. Oh, it seemed you probably did some of these. So yeah,
Yeah.
physical
Mhm.
discretes, chemistry discretes, things like that. Well, it seems like you did a bunch of them. What, were you asking for like more questions like this or?
Oh, I was just like, yeah, I was just wondering in general, like, because I see like the unit questions lots of like what were the kind of ones I should like just have stuck in my brain, but yeah.
Yeah, yeah, yeah. I would say. Um. Oh yes. So we didn't really talk about Anki, but um, would you be open to to using it?
Yeah, I think I realized that I can't avoid it, so
Because the like the utility in it is
yeah.
that like any other flashcard system, Anki, depending on how well you know a card, will alter the frequency that you see it. So if it's something you
Mm,
think it's easy, you press easy, it won't show it to you for like 10 weeks or something. But if you think it's hard, it'll show it to you like in 10 minutes. So it automatically sorts it. So at first it might seem like, oh my God, there's 2,700 cards that I have to memorize, but it's going to ultimately like sort itself
mm,
out. So it's not going to take that long. Um, and also don't worry about like finishing it. Like I kind of
mhm.
say that about like UWorld also. Like I basically just tell my students to do, and that reminds me, I'm gonna make like a study schedule kind of like
Yeah, I
spreadsheet
think
for
that'd be
you.
helpful.
Yeah, yeah, yeah.
Yeah.
Because I make it for all my students,
Uh,
um, but I usually just have for like each day,
mm,
like Anki 45 minutes to an hour.
mm,
And I do it in terms of time because if it otherwise like it can really like snowball. Like if you miss a
yeah.
day, it could be like you have 3,000 cards due, and then you don't want to waste a day doing just Anki. So yeah, you could play around with that. Maybe start like 15 minutes a day. We can work you up to like 45 minutes to like an hour. I'll make the spreadsheet for you and you can like it'll be like it's like a kind of like a calendar thing. You could like
Mhm.
even strike through the things that you did. But yeah, I would say to yeah, get Anki, and one of like the fastest things like if you're using I think it's the Miles Down deck.
Yeah.
But they're all pretty much the same, but there's like a deck within that called Essential Equations,
Mm.
and I'm pretty sure that includes like the units as well.
Okay.
So, I mean, yeah, you might know that already, but yeah, that could give you a good like intuition for unit conversions and being able to do like that dimensional analysis uh
Hmm.
really well. I'll say
Yeah.
like for like a homework problem, um, a kilowatt hour is a unit of what? And when I say what, I mean like I don't mean like specific. I mean like is it like power? Is it like
Mhm.
energy? Is it like blah blah blah?
Is it energy?
What do you what do you think?
Because watt is like power, which is energy over time, and then if you're multiplying that by time, so equals to power. Okay.
Great job. Yeah, great job. Great job. Awesome. That's you got it.
Okay,
Good.
sounds good. Yeah.
Good stuff. Okay, so let's see. What next?
Yeah, I guess that's also my follow-up question. So, because right now what I have is like, yeah, there's the UWorld, and then I took like I think 5 Jack Westins at this point. Haven't really, yeah, done like a full, content like review of them like I have with you right now. Which is like I think this is more helpful because there's some areas like the magnetic field where it's just I don't think I would have figured that out on my own.
Oh
So,
yeah, yeah. We should
yeah.
probably like
Mhm.
have some like dedicated sessions like whenever you
Mm.
have seen like enough biochem stuff that you aren't familiar with or physics stuff, we could probably like knock that stuff out really quick. Um, so your basic day, like you're doing like UWorld stuff, Jack
Yeah,
Westin stuff.
like right now it's like a little like kind of
Hmm?
up to flow because I still have to also study for school finals, but I'm at least carving out like at least 2 to 3 hours. So yeah, for now it's just been like U World and then just adding on the mistakes to like my mistake diagram and that's about it. But yeah, I'm just kind of focusing on one area, which is like the amino acids.
Okay, okay.
Mhm.
Got it, got it. Um,
Yeah, I can send you like a screenshot of like I
yeah,
guess my U World like which subsections I've finished.
yeah. So yeah, I'll send it in the email also,
Mm.
but like for amino acids, like you want to be able to identify an amino acid from like just its structure
Mhm.
and like by extension identify how something can behave based on like functional groups. Um, but yeah, I'll talk more about that in like an email.
Yeah, sounds good. Yeah, I can
All
definitely
right.
send over some of like more data on my end, but yeah.
Yep. All right, let's see. So how did you want to
Mm.
do
I think
the
between like now and like next week, I'm thinking of probably like squeezing in like one more session like this, perhaps, or one or two, and then yeah, over winter break having like a lot more time.
okay,
But probably next week is more like school focused.
got it.
Mm.
How did you want to do like the payment?
Oh
Was it
yeah,
like
yeah. What do you so
Zelle?
I do you have
Oh,
Venmo?
what's that?
Do you have Venmo?
Yeah. Okay, I'm putting in the chat my Venmo.
Mhm.
The YouTube rate. So I think that'll be like 128. Does that work?
Oh, I thought, wait, was it 85 an hour or?
Oh yeah. I mean, we did an hour and a half, but it's okay. We
Oh,
could do the 85. That's fine.
okay. Are you sure? Thank you.
It's fine. It's fine.
Sorry, I didn't realize the time, but
Mm-hmm.
okay. I think oh, it's asking for the 4 digits of the phone number.
Oh yeah, here.
Okay, I just paid.
I got it.
Uh, Thank you so much.
Yeah, awesome. It's great meeting you. We're gonna crush this.
Yes.
All
I
right.
think I'm like fully like devoted towards it. It's just more how like the structure and then also like your guidance. I think it's gonna
Yeah,
go. Yeah.
yeah. All right. Take care. Great meeting you. See
Yeah,
you.
thank you so much again.
Yep.